Hello, this will be a demonstration of proposition 2 from book 3 of Euclid's Elements, which states that if on the circumference of a circle 2 points be taken at random, the straight line joining them will fall within the circle. All we are given is a circle ABC. Let's call this A, let's call this B, this will be C. That's all we are given, and points A and B are chosen randomly on them. And what we have set out to prove is that the straight line joining A and B will fall within the circle ABC. So it'll fall somewhere in here, not outside and not on the circumference. It must fall within. Now, if this is not the case, if AB does not fall within the circle ABC, let's say it falls outside as the straight line AEB. This is a straight line, AEB. Okay? Next, we shall simply take the center of the circle ABC. We shall call this point D. And we shall join DA, DB, and DFE such that the point F is where DE and the circumference of ABC intersect. Now, we know that DA is equal to DB. Oh, I should have said for the last step, we can take the center by proposition 3.1, and we can join straight lines by postulate 1. Now, we know that DA and DB must be equal, for they are radii of the same circle, so by virtue of definition 115, we know they must be equal. And being two equal sides in the triangle DAB, which is that triangle, we know that the angles which they subtend must also be equal. That is to say that the angle DAE is equal to the angle DBE, like so. We know this by proposition 1.5. Now, we also know that the angle DEB is greater than the angle DAE, DEB being that angle right there. And we know it is greater than the angle DAE because it is exterior. It is an exterior angle to the triangle DAE, and so it must be greater than any interior angle, in this case, DAE. We know this by proposition 1.16. And then, by a property of magnitudes, we can say that the angle DEB must also be greater than the angle DBE. And we also know that because the greater side subtends the greater angle, or the greater angle is subtended by the greater side, we can say that the side DB, which subtends the greater angle DEB, must itself be greater than DE, which subtends DBE. So that is this straight line here, DE, must be greater than this straight line here, DB. We also know, by virtue of the same definition, definition 1.15, that DB and DF must be equal. And again, by a property of magnitudes, we are then allowed to say that the straight line DF is greater than the straight line DE. Now, we also know by common notion 5 that the part must be less than the whole. We can also say that the straight line DF is also less than the straight line DE. And so we have arrived at the conclusion that the straight line DF is simultaneously greater to and less than the straight line DE, which is absurd. And so we can then say that the straight line AB will not fall outside the circle ABC. Similarly, we can also prove that the straight line AB will not fall on the circumference of the circle ABC, and so falling neither outside the circle nor on it, it must fall within. And so we can rightly say that the straight line AB must fall within the circle ABC, therefore, etc., QED. Again, I don't have anything unique to say about this proposition, so I will simply move on to proposition 3.3.